The universe began in total darkness. We are about to journey to the very edge of time to uncover 30 mysteries of the first stars and galaxies. By the end, you will understand how our entire cosmic story might be rewritten. We will find out why the first stars could have been true monsters and how their ghostly light might still be detected today. What part of this ancient, vanished cosmos intrigues you the most? Our story begins not with a bang, but with a profound and lasting silence. After the brilliant flash of the cosmic microwave background faded into invisible radio waves, the universe entered its longest night. This is the era cosmologists call the Cosmic Dark Ages, a mysterious span of time lasting hundreds of millions of years where not a single star shone. It was a universe of pure potential, filled with a primordial soup of simple hydrogen and helium gas, all woven through with the invisible threads of dark matter. In this perfect blackness, light as we know it could not travel freely. Any photon emitted would almost immediately be swallowed again by another atom, trapped in a constant cycle of capture and release. This made the entire cosmos an opaque fog, a featureless void to any outside observer. Yet within that fog, the seeds of our future were quietly stirring. Tiny ripples in density, imperfections left over from the universe's explosive birth, were the only game in town. Gravity, patient and relentless, began to favor these slightly denser patches. Atom by atom, over incomprehensible stretches of time, these specks gathered more mass. The Dark Ages were not an empty pause, but a crucial incubation period. It was the universe gathering its breath, concentrating its raw materials, and preparing for a transformation. For astronomers today, this presents a monumental challenge. How do you observe an era that produced no light to see? It is a blind spot in our history, a silent chapter we must piece together through theory and by studying the echoes it left in the universe that followed. This darkness holds the key to our very existence, for within it the first structures were born. Gravity's patient work in the dark finally reached a tipping point. Within those densest knots of primordial gas, a new kind of furnace ignited, ending the cosmic night forever. This brings us to our second great mystery, the nature of the universe's very first generation of suns. Astronomers call them population 3 stars, and they were likely unlike anything shining in our sky today. Born from the pure, untainted hydrogen and helium of the early cosmos, they contained not a single speck of the heavier elements we call metals. This purity had staggering consequences. Without metals to help the gas clouds cool and fragment efficiently, these first stars could gorge themselves on the surrounding material, growing to truly monstrous sizes. Current theories suggest a population 3 star could easily be 100 or even several hundred times more massive than our own sun. Think of a star so colossal it would make our sun look like a tiny ember in comparison. Such a star would burn at a ferocious temperature, a blazing blue-white beacon in the newborn universe, but this brilliance came at a terrible cost. Fueling such an immense nuclear reactor required consuming its fuel at a breakneck pace. Where a star like our sun will shine steadily for billions of years, a massive population 3 star might live for only a few million, a cosmic firework that flared spectacularly and died young. Their pure composition meant their deaths were just as unique as their births. With no heavier elements to seed future solar systems, these stars could not form rocky planets like Earth. Around a population 3 star, there would be no asteroids, no comets, and certainly no possibility for life as we know it. Their entire purpose, it seems, was to act as the universe's first alchemists. Their violent deaths in colossal supernova would forge the first heavy elements, from carbon and oxygen up to iron, and blast them out into space, polluting the pristine cosmic gas. This enriched material would then become the building blocks for the next generation of smaller, longer-lived stars and eventually for planets and us. Yet here lies the core of the mystery. For all their importance, we have never definitively seen one. Population 3 stars remain a ghost in our equations, a brilliant prediction at the very foundation of cosmic history that still awaits its first direct observation. Finding even a single survivor or catching the echo of its death would be one of the greatest discoveries in all of science, confirming our deepest theories about how everything began. The death of those first giants was the very event that made our existence possible. But to understand their birth, we must step back into the darkness one more time to confront a third and equally profound mystery. How did the first stars even begin to form in a universe that lacked the very ingredients we consider essential for star birth today? In our modern cosmos, stellar nurseries are rich with dust. Think of the beautiful, dark lanes in the Orion Nebula, those tiny grains of silicon and carbon forged in earlier stellar generations are cosmic refrigerators. They absorb heat from a collapsing gas cloud and radiate it away as infrared light, allowing the cloud to cool, shrink, and fragment into dozens, even hundreds of smaller stars. It is an efficient, bustling factory. Now strip all of that away, go back to the pure hydrogen and helium gas of the early universe. There is no dust, no carbon, no oxygen. There are no metals at all to help the cloud shed its heat. So how does it cool down enough to collapse? The answer lies in a fragile and simple molecule, molecular hydrogen. Two hydrogen atoms binding together. When this molecule forms, it can vibrate and rotate, releasing a tiny trickle of energy in the form of infrared light. It is an incredibly inefficient cooling system compared to dust, like trying to cool a roaring furnace by blowing on it with a thin straw. But in that pristine cosmos, it was the only straw available. This slow, leaky cooling had a dramatic effect on the scale of star formation. Without the ability to shed heat quickly, a vast cloud of gas could not easily break apart. Instead of fragmenting into many pieces, it likely collapsed as one single, monstrous entity. Picture a mountain of gas, hundreds of times the mass of our Sun, slowly and inexorably condensing under its own weight. The complex computer simulations that model this process are like digital time machines. They show turbulent rivers of pristine gas, guided by the invisible scaffolding of dark matter halos flowing together over millions of years. Within these simulations, you do not see a sparkling cluster of newborn stars emerge. You see one dominant, dense knot of gas growing ever hotter and denser at the heart of the cloud, while the rest of the material feeds it in a relentless, spiraling dance. This leads to the precise trigger of the mystery. What was the final push with cooling so sluggish? What tipped the balance from a slowly condensing cloud to a runaway collapse that ignited nuclear fusion? The simulations suggest it was a delicate threshold. Once the gas density reached a certain critical point, the molecular hydrogen cooling, as inefficient as it was, finally allowed the core to lose just enough heat to catastrophically give way. It was a tipping point, a moment of no return for the universe. The birth of that first light was not a gentle flicker, but the violent, singular ignition of a behemoth, a lone titan emerging from a cosmic womb of unimaginable scale. This solitary nature of the first stars stands in stark contrast to the stellar families we see today, raising a haunting question: did the first stars always die alone? But that solitary giant did not shine into an empty void. Its light, especially its most powerful ultraviolet radiation, began a journey that would transform the entire cosmos, and we can still find the echoes of that transformation etched into the light of even more distant objects. This brings us to our fourth great mystery, a phenomenon so beautiful and complex it is called the Lyman Alpha Forest. To understand it, we must become cosmic archaeologists, learning to read a fossil record written not in stone, but in ancient light itself. The key is the quasar, the brilliant core of an ancient galaxy powered by a voracious supermassive black hole. Quasars are the universe's ultimate lighthouses, beaming intense light across billions of light years. When astronomers point their telescopes at a quasar and break its light into a rainbow-like spectrum, they do not see a clean, continuous band of color. Instead, they see a stunning pattern of dark lines, like a barcode stamped across the light. Each one of those lines is a signature of a specific atom, absorbing a very precise color of light. For the early universe, the most important signature comes from neutral hydrogen, the most abundant element. Hydrogen absorbs light at a very specific ultraviolet wavelength known as the Lyman alpha line. Now, imagine the quasar's light beginning its epic journey toward us. As it travels, it passes through countless clouds and filaments of neutral hydrogen, gas that float in the vast spaces between galaxies. Each time the light passes through one of these clouds, the hydrogen atoms within it greedily snatch away that specific Lyman alpha wavelength, creating a single dark absorption line in the quasar spectrum. But here is the truly magical part. The universe is expanding, which stretches light, making it redder. A hydrogen cloud that is very far away, and thus seen as it was very long ago, has its absorption line stretched a little bit. A cloud that is closer to us from a more recent cosmic time has its line stretched a little bit more. So, a single beam of quasar light traveling through billions of years of cosmic history collects a unique series of absorption lines, each one redshifted by a different amount, corresponding to the distance of the cloud that created it. The result is not a single line, but a dense, intricate forest of lines in the spectrum. This Lyman alpha forest is a direct three-dimensional map. It is a fossil record of the distribution of neutral hydrogen gas throughout cosmic time. By reading this forest, astronomers can reconstruct the cosmic web in its infancy, seeing the filaments and voids that existed long before galaxies took their modern shapes. The mystery lies in decoding this intricate pattern. The depth and shape of each line tells a story about the density, temperature, and motion of the gas cloud that created it. Was the gas calm and diffuse, or turbulent and collapsing? Was it still neutral, or had it been blasted by radiation from a nearby first star or galaxy and become ionized? The forest holds the answers. It is our most powerful tool for witnessing the epoch of reionization in action, the great cosmic dawn when the first starlight began to burn away the primordial fog. By studying these ghostly lines, we are not just looking at ancient light. We are tracing the very architecture of the young universe and listening to the echoes of its first awakenings. That beautiful, intricate forest of absorption lines holds a secret history of destruction. It tells the story of a universal phase change so profound it altered the very fabric of space, a mystery we call the epoch of reionization. For hundreds of millions of years after the Big Bang, the cosmos was filled with neutral hydrogen gas, where each atom's single electron was peacefully bound to its proton. This was the opaque fog of the Dark Ages. Then the first stars and galaxies ignited. Their brilliant, high-energy ultraviolet light acted like a cosmic ultraviolet laser blasting through the darkness. Each photon carried enough energy to violently strip electrons from those neutral hydrogen atoms, turning them into free-floating protons and electrons, a state we call ionized plasma. This process, reionization, was the universe's final act of clearing the fog. It made the vast reaches of intergalactic space transparent to light, a necessary step for the universe we see today. But the details of this great awakening are hotly debated. When exactly did it begin? Did those first monstrous population 3 stars flicker on and start the process incredibly early? Or did it require the collective effort of billions of smaller galaxies that came later? And how long did it take? Was reionization a swift, dramatic event, like a sudden sunrise burning off a morning mist? Or was it a slow, patchy process, with bubbles of ionized gas slowly growing and merging over hundreds of millions of years? The sources of the ionizing radiation are another core puzzle. Did a few brilliant, rare quasars powered by supermassive black holes do most of the work? Or was it the combined ultraviolet hum from countless faint early galaxies, a democratic effort from the first cosmic neighborhoods? Astronomers are detectives on this case using two primary clues. The first is the cosmic microwave background, that fossilized light from the infant universe. Subtle patterns in its polarization tell us when the bulk of reionization was likely finished, because scattering off free electrons left a specific imprint. The second clue comes from those distant quasars and their Lyman alpha forests. By studying how complete the absorption is at different distances, and thus different cosmic times, we can map when the neutral hydrogen fog was finally burned away along a given line of sight. The current evidence paints a fascinating, if messy, picture. Reionization likely began around when the universe was a few 100 million years old and was largely complete by the time it reached 1 billion years. It was probably a gradual, uneven process driven primarily by early galaxies, not quasars, but the timeline remains fuzzy and the exact contributors are still unknown. This universal phase change was not just about making space transparent. It heated the intergalactic gas, changing how easily future galaxies could pull in material to grow. It was a fundamental environmental shift that set the rules for everything that came after. Pinpointing exactly how and when it happened is essential, because it directly tells us about the nature and timing of the universe's very first sources of light. Their ghostly ultraviolet beams, long since faded, left a permanent scar on the cosmos, and we are just learning how to read it. The great reionization of the cosmos did more than clear a universal fog. It may have permanently silenced the faintest voices in the cosmic chorus. This leads us to a mystery that hits closer to home, a puzzle in our own galactic backyard known as the missing satellite problem. Our current and highly successful model of the universe, called Lambda CDM, uses supercomputers to simulate how dark matter and normal matter should have clumped together from the Big Bang to today. These simulations are breathtakingly detailed, painting a picture of a cosmos where every large galaxy, like our Milky Way, should be surrounded by a vast swarm of thousands of smaller dwarf satellite galaxies, each held in orbit by its own little halo of dark matter. It is a prediction that feels robust and elegant, yet when astronomers look up, they find a stark contradiction. Instead of thousands of dancing companions, we have only observed a few dozen faint dwarf galaxies around the Milky Way. The overwhelming majority of those predicted satellites are simply not there. This is not a minor accounting error. It is a glaring discrepancy that challenges the very foundations of our understanding on the smallest cosmic scales. So where did all those galaxies go? One compelling solution points directly back to the harsh environment created by the first stars and galaxies. Imagine one of those predicted tiny dark matter halos in the early universe. It begins to slowly gather its own little pocket of hydrogen gas, poised to become a faint miniature galaxy. But then the epoch of reionization begins. A flood of ultraviolet radiation from the larger, more powerful first galaxies nearby comes screaming through. For a massive galaxy with a strong gravitational pull, this radiation is a nuisance, blowing away some gas from its outer edges. But for a tiny, fragile dwarf halo with much weaker gravity, it is an existential catastrophe. The intense radiation heats the gas to extreme temperatures, giving its atoms enough energy to achieve escape velocity. In a dramatic event astronomers call photoevaporation, the entire gaseous reservoir of the proto-dwarf galaxy can be blown clean away, like a candle being snuffed out by a hurricane. With its gas gone, the dwarf halo is left dark, barren, and invisible. It is a ghost galaxy, a skeleton of dark matter with no stars to light it up. This could explain the missing satellites. They are not missing at all. They are all around us, but they are completely dark, detectable only by the subtle gravitational tug they might exert. Another possibility is even more fundamental. Perhaps our understanding of dark matter itself needs a tweak on these small scales. The standard model assumes dark matter is cold and moves slowly, clumping easily into these myriad small halos. But what if some dark matter is slightly warmer, giving the particles more motion? That extra jitter would smooth out the smallest clumps, preventing thousands of the tiniest halos from ever forming in the first place. This missing satellite problem is a powerful reminder that the universe's first acts of creation were also acts of ruthless selection. The same brilliant dawn that ignited the first galaxies may have doomed countless others to eternal darkness, leaving us with a silent sky where our theories still hear a deafening echo of what should be. These ghostly dark matter halos are not the only cosmic phantoms we seek. Our greatest ambition is to witness the birth of light itself, to capture the direct glow of the very first stars. This is the monumental challenge that defines modern observational cosmology. The light those primordial beacons emitted was a brilliant, searing ultraviolet. But that was over 13 billion years ago. In the eons since, the relentless expansion of the universe has stretched that light on an incredible journey. Its wavelengths have been pulled like a cosmic taffy from the ultraviolet through the visible spectrum, all the way into the far infrared and even the microwave regime. What began as a piercing blue flash has been transformed into a feeble, deep red heat signature, and it is not just transformed, it is incredibly faint. The combined glow of all those first stars and galaxies is now an ancient whisper, a signal billions of times weaker than the blinding infrared light produced by dust in our own Milky Way galaxy. Trying to detect it is the ultimate needle in a haystack search, where the haystack is also glowing brightly and constantly moving. It is the astronomical equivalent of trying to hear a single, soft whisper from across a crowded, roaring stadium. So how do we even attempt such an impossible task? The answer lies in escaping our planet's obscuring atmosphere and building telescopes of unprecedented sensitivity, designed specifically to listen for this cosmic dawn. The recently launched James Webb Space Telescope is our first great hope in this hunt. With its giant gold-coated mirror and suite of infrared instruments chilled to incredibly low temperatures, it is the most powerful time machine ever built. Webb is peering back at the very first galaxies, looking for the signatures of those early, massive stars in their collective light. But the ultimate quarry, the diffuse background glow from the very first stars that formed before galaxies assembled, may require an even more specialized tool. Scientists are already planning for the next leap, a concept called the Origins Space Telescope. Imagine a telescope so cold and so sensitive it could map the sky in the far infrared with hundreds of times more clarity than any prior observatory. Its goal would be to isolate that specific whisper of heat from the cosmic dawn, separating it from the local infrared fog of our solar system and galaxy. The mystery is whether the signal is even there to be found in a form we can recognize. Could the light from the first stars be so tangled with the emission from the first black holes and the heated dust of later generations that it creates an inseparable murk? Or will we one day point our instruments at a seemingly dark patch of sky, subtract everything we know, and find a residual, uniform glow, the faded signature of the universe's first sunrise? Finding that signal would be more than a detection. It would be a direct photograph of creation, a moment when theory becomes tangible history, and the darkness of the cosmic dawn finally gives up its oldest secret. But that faint infrared whisper is not the only signal from the dawn. There is another, far more violent and energetic signature we must confront, one that points to an even deeper mystery. At the very heart of some of the most distant quasars, we find supermassive black holes already weighing billions of times the mass of our Sun, yet we see them shining brightly when the universe was less than 1 billion years old. This presents a cosmic timing problem of staggering proportions. Think of a normal stellar mass black hole, the kind left behind when a massive star explodes. It starts with perhaps 10 or 20 solar masses. To grow into a billion solar mass monster, it must feast on gas at a ferocious rate for nearly its entire existence. But there is a speed limit called the Eddington limit, which governs how quickly a black hole can consume material before its own radiation pushes the surrounding gas away. Even if a black hole ate at this maximum possible rate from the very moment it formed, the math struggles to explain how it could become so unimaginably large in such a tiny sliver of cosmic time. It is like finding a fully grown ancient redwood tree in a forest that is only a few years old. The seed must have been enormous from the start, so what planted these monstrous seeds? Astronomers have several compelling and frankly unsettling theories. The first candidate comes from the death of those first stars. If a population 3 star was truly colossal, say several hundred solar masses, its core collapse might not produce a typical supernova. Instead, the entire star could implode directly into a black hole with a starting weight of maybe 100 solar masses. That is a hefty seed, but it still needs to grow a billion-fold. A more extreme idea is the direct collapse black hole. Imagine a vast cloud of pristine gas in the early universe collapsing under its own weight, but instead of fragmenting to form many stars, something prevents it from cooling. Perhaps it is bathed in the intense ultraviolet light from a nearby first galaxy, which keeps the hydrogen atomic and hot. This hot, monolithic cloud collapses directly, catastrophically, into a single object. The result could be a black hole seed with a mass of 10,000, even 100,000 suns right from birth. That is a seed with a head start. Another possibility looks to the first dense star clusters. In a packed stellar nursery, massive stars could collide and merge, building up a central object that quickly collapses into a medium-sized seed. And then there is the most exotic candidate of all, primordial black holes. These would not be born from stars at all, but from the extreme density fluctuations in the very first fractions of a second after the Big Bang. If conditions were just right, pockets of space could have simply pinched off into black holes of almost any size. One of these, with the mass of a large asteroid or a small moon, could have served as a seed, slowly accreting mass over time. Each pathway tells a different story about the infant universe. Did galaxy formation begin with a brilliant first generation of stars whose deaths left behind the first black hole seeds? Or did the black holes come first, with their immense gravity pulling in the gas that would later form the first stars around them? The quasars we see are the screaming evidence that one of these theories must be true. Their existence forces us to accept that the cosmos found a way to build titans in the blink of an eye, and we are still searching for the blueprint. Those screaming quasars were built from the very atoms their stellar ancestors forged in fire. This brings us to a mystery that is literally written into our own bodies, the origin of the first heavy elements. For over 100 million years, the universe's periodic table was pitifully simple, containing just hydrogen, helium, and a trace of lithium. Everything else, every atom of carbon in your cells, the oxygen you breathe, the iron in your blood, had to be manufactured from scratch inside the furnaces of stars. The first stars were the universe's pioneering alchemists, and their recipe was one of unimaginable pressure and heat. Inside the searing core of a massive population 3 star, the nuclear fusion process did not stop at helium. Under crushing gravity and temperatures exceeding 100 million degrees, helium nuclei themselves began to fuse. 3 helium atoms could smash together to form carbon. Adding another helium atom created oxygen. In a stepwise chain known as stellar nucleosynthesis, these giants cooked elements up the periodic table: neon, magnesium, silicon, and finally, at the very end of the line, iron. Creating iron, however, was a cosmic dead end. Fusing iron does not release energy, it consumes it. So when a star's core finally becomes a ball of iron, the fusion factory shuts down for good. The star's fate is sealed. For these first massive stars, death was not a quiet fade. their immense gravity, no longer held back by the outward pressure of fusion, caused the core to collapse in a fraction of a second. The rebound from this collapse triggers a cataclysmic supernova explosion, blasting the star's outer layers, now enriched with these newly forged heavy elements, out into space at nearly the speed of light. But for the very largest of the first stars, theorists propose an even more spectacular finale, a pair instability supernova. In these monsters, the core becomes so hot that light itself begins to spontaneously create matter and antimatter particle pairs. This saps the core's pressure almost instantly, causing a runaway collapse and a thermonuclear explosion so utterly violent that it completely obliterates the star, leaving behind no black hole or neutron star, just an expanding cloud of pure, freshly minted elements. This is the moment of cosmic enrichment. The pristine gas of the early universe, for the first time ever, is polluted with metals, but here lies the core of the mystery. How did this pollution spread? Was the debris from a single supernova enough to seed an entire neighboring gas cloud, triggering the birth of a second generation of slightly metal-rich stars? Or was much of this precious material ejected into the vast, empty voids between galaxies, lost forever to future star formation? The answers are hidden in the oldest stars we can find, right here in the Milky Way's halo. Stars like He 0107-5240, a faint ancient sun with an iron content over 200,000 times lower than our sun's. It is a living fossil, a second-generation star that formed from gas enriched by perhaps just one single population 3 supernova. By dissecting its light, astronomers can read the specific chemical fingerprint of that one explosive event, like finding a single ash from the universe's first campfire. The precise mix of elements in these ancient stars tells a story. A high ratio of carbon to iron might point to the unique nucleosynthesis of a pair instability supernova. The presence of certain heavier elements like strontium might indicate that the star's birth cloud was also seeded by the debris from a neutron-star merger, a later but equally crucial cosmic forge. Each ancient star is a time capsule holding a chemical record of the very first acts of creation, the moments when the universe went from simple to complex and set in motion the possibility of everything that was to come, including us. Those ancient stellar fossils give us a chemical record, but to see the full picture we must look at the architecture of the first cities of stars. This brings us to our 10th mystery, the true nature of the first galaxies themselves. Were they just tiny, chaotic blobs of newborn suns, or could they have been surprisingly mature and structured from the very beginning? With the Hubble Space Telescope, and now with the revolutionary James Webb Space Telescope, we are finally getting our first clear glimpses of galaxies as they existed in the universe's first few 100 million years. What we are finding is deeply puzzling. Some of these early galaxies appear exactly as our simplest models predicted, small, irregular, and clumpy, like splatters of luminous paint against the dark canvas of space. They are the cosmic equivalents of toddler scribbles, full of energy but lacking clear form. Yet others, seen at similarly ancient epochs, present a shocking sight. They show hints of disks, central bulges, and even what appear to be spiral arm structures, all emerging at a time when the cosmos was only a few % of its current age. This is like finding a perfectly engineered modern skyscraper in the ruins of a prehistoric settlement. How could gravity assemble such ordered, rotating systems so quickly? In our standard story of cosmic evolution, structure forms hierarchically. Small things merge to form bigger things. First, tiny dark matter halos form. They attract gas, forming the first stars and protogalaxies. Then, over billions of years, these small building blocks collide and merge, their orbits gradually settling into the majestic disks and spirals we see in galaxies like our Milky Way. That process is supposed to take time, lots of it. The discovery of what look like mature galaxies in the infant universe suggests this orderly timeline might be wrong. Perhaps the early universe was a more efficient architect. One possibility is that the dark matter halos in the dense early cosmos were inherently different, spinning in a way that encouraged gas to settle into disks almost immediately upon falling in. Another, more unsettling idea is that we might be misinterpreting the fuzzy, redshifted images. A clumpy, irregular galaxy viewed from a certain angle, with its light stretched and smeared by cosmic expansion, might accidentally resemble a rotating disk. Or perhaps what we are seeing is not a single, stable galaxy at all, but the blinding glow of two smaller galaxies caught in the act of a violent merger, their collision creating a temporary illusion of structure. Determining the true morphology of these first galaxies is not just an academic exercise. It is a direct test of our fundamental understanding of how the cosmos builds itself. If disks and spirals truly existed that early, it forces a rewrite of the galactic growth chart. It means the universe could skip steps, achieving a kind of cosmic maturity in a fraction of the expected time. Every faint, red smudge from the dawn holds the answer, and with each new Webb observation, we are getting closer to knowing whether the first galaxies were messy nurseries or surprisingly well-organized homes for the very first stars. That ancient light from the first galaxies is only part of the story. There is another, far more elusive signal humming through the cosmos, one that could let us tune a radio to the birth of the first stars themselves. This is the mystery of the cosmic hydrogen 21-centimeter signal. The physics behind it is beautifully simple. A hydrogen atom in its neutral state is just one proton and one electron. Both of these particles act like tiny magnets, and they can spin in relation to each other. Most of the time, the electron and proton spins are aligned. But very, very occasionally, the electron will spontaneously flip, switching to the opposite spin. This tiny quantum jump releases an incredibly specific amount of energy, which escapes as a radio wave with a wavelength of precisely 21 centimeters. It is an extremely faint whisper from a single atom, but hydrogen is the most abundant thing in the universe. If you could build a radio telescope sensitive enough to map this signal across the sky, you would have a perfect three-dimensional map of all the neutral hydrogen gas throughout cosmic history. You could watch the dark ages in real time, see the bubbles of ionized gas from the first stars begin to grow, and witness the entire epoch of reionization unfold like a cosmic film strip. It is the ultimate dream for cosmologists. The challenge, of course, is that this signal is phenomenally weak, buried under a cacophony of radio noise from our own galaxy, the Earth's atmosphere, and even our own electronics. To hunt for it, scientists have built some of the quietest radio antennas on Earth, in remote deserts like the Australian outback and the South African Karoo. One pioneering experiment, called EDGES, made a claim that sent shockwaves through astrophysics. After years of painstaking data collection, the EDGES team reported they might have detected the very oldest part of this 21-centimeter signal, a fingerprint from when the universe was only around 180 million years old. But the signal was not just there, it was profoundly strange. It was an absorption signal, meaning the ancient cosmic hydrogen appeared colder than the cosmic microwave background radiation bathing it. That is expected, but the depth of the dip was about twice as strong as any standard model could explain. The early gas, it seemed, was shockingly, inexplicably cold. This single observation, if confirmed, threatens to rewrite fundamental physics. One leading explanation is that this primordial hydrogen was cooled by interacting with something else, something cold and pervasive. The prime candidate, dark matter. In our standard models, dark matter and normal matter interact only through gravity. They pass right through each other like ghosts. But what if, in the ultra-dense early universe, dark matter particles could bump into hydrogen atoms, transferring heat away? This interaction would have chilled the gas dramatically, creating the deep absorption dip EDGES saw. It would be the first non-gravitational fingerprint of dark matter ever detected, a monumental breakthrough. the entire field is now holding its breath because the result is controversial. Other experiments have not yet confirmed it, and the signal is so strong that some worry it could be a subtle artifact of the instrument itself or local interference. The next generation of telescopes, like the colossal square-kilometer array, is being built with this mystery as a primary target. With thousands of radio dishes working in unison, it will have the sensitivity and precision to map the 21-centimeter signal across vast cosmic times. It will either definitively confirm the edge's anomaly, unveiling a new chapter in particle physics, or it will reveal it as a tantalizing mirage. Either way, the quest continues, listening for a whisper from the dawn that might tell us not just about the first stars, but about the true nature of the invisible substance that shapes our cosmos. That faint radio whisper from the dawn is a direct probe of the universe's hidden architecture, an architecture built not from stars or gas, but from something we cannot see. This brings us to the silent partner in creation, the indispensable yet invisible force that dictated where the first stars could ever form: dark matter. Without it, our cosmos would be a formless, empty void. Dark matter provided the gravitational skeleton for everything we see. In the early universe, slight overdensities in this mysterious substance, amplified by gravity, grew faster than the normal matter because they were not slowed by radiation pressure. These dark matter clumps became the seeds of the cosmic web, a vast, interconnected network of filaments and nodes stretching across the emptiness. Within this web, dark matter halos formed ghostly spheres of invisible mass that acted as gravitational traps. Only then could the normal baryonic matter, the hydrogen and helium gas, begin to flow. Picture a mountain range sculpted from a material you cannot touch. The normal gas is like water vapor in the atmosphere, condensing and flowing down into the valleys and basins carved by the dark matter peaks. Those dark matter valleys were the crucibles. They gathered and concentrated the fuel, creating the dense, pressurized environments where gas could finally collapse under its own weight and ignite the first stars. In this story, dark matter is the ultimate cosmic real estate developer, deciding where the first luminous cities would be built, but its role may have been even more active. One profound mystery asks if dark matter itself could have provided an early heat source. Some theories suggest dark matter particles, when they collide, could annihilate each other, releasing energy. Or perhaps they slowly decay over time. If this happened in the dense cores of the first dark matter halos, that extra injection of heat could have significantly warmed the primordial gas. This would be a double-edged sword. A little heat might prevent the gas from cooling too quickly, affecting the ultimate size of the first stars. Too much heat, and it could completely stifle star formation, delaying the cosmic dawn. The timing and intensity of the first starlight could therefore be a direct clue to the particle nature of dark matter itself. Another puzzle lies in the texture of the dark matter. Our standard model assumes it is cold, meaning its particles move slowly, allowing it to clump on even the tiniest scales. This predicts a universe filled with countless small dark matter halos. But what if dark matter is slightly warm, with particles that have a bit more speed? That extra motion would smooth out the smallest clumps, erasing the tiniest gravitational wells. The result would be a delay. Star formation might only begin in larger, rarer halos that took longer to assemble, pushing back the entire timeline of cosmic dawn. We are searching for these imprints in the patterns we see, the distribution of the earliest galaxies across the sky, their clustering, and even their internal properties are a fossil record of dark matter's fundamental character. By studying the first structures, we are not just looking at ancient stars, we are conducting a grand particle physics experiment across billions of light years, using the universe itself as our laboratory. The invisible architecture of dark matter set the stage, but the final act of those first stars was a spectacle of pure, self-destructive fury. For the very largest of the population, three behemoths, those weighing between 130 and 250 times our Sun, death was not a collapse into a black hole. It was a complete and total annihilation. This theorized fate is known as a pair instability supernova, and if it occurred, it would rank among the most powerful explosions the universe has ever produced. To understand its violence, we must venture into the star's core in its final moments. The temperature there is so unimaginably high, exceeding 1 billion degrees, that the radiation itself transforms. The gamma rays flying around are no longer just light. They are packets of pure energy so dense they spontaneously create matter. Specifically, a gamma ray photon can convert itself into an electron and its antimatter twin, a positron. This act of creation is the star's undoing. Those gamma rays were providing outward pressure, helping to hold the star up against its own immense gravity. When they vanish, replaced by these particle pairs, the supporting pressure suddenly drops. The core finds itself in a catastrophic predicament. It is as if the foundation of a skyscraper instantly turned to smoke. With nothing to hold it up, the core collapses inward at a significant fraction of the speed of light. This implosion is not gentle. It compresses and heats the core even further until it reaches a point of thermonuclear overload. The infalling material rebounds in a runaway fusion explosion of unimaginable scale. The entire star, from core to outer layers, is not just blown apart, it is utterly vaporized. Every single atom is fused into heavier elements and then blasted into the void at incredible speeds. No compact remnant is left behind, no black hole, no neutron star. The star simply ceases to exist, leaving only an expanding cloud of stellar ash. This is the ultimate cosmic firework, a single flash that for a brief moment could outshine an entire galaxy of later stars. The mystery for astronomers is whether we have ever witnessed the aftermath of such an event. The key lies in the unique chemical signature this explosion would leave. Because the entire star is fused and ejected, the elemental mix is special. A pair instability supernova would produce enormous amounts of intermediate mass elements like silicon, magnesium, and calcium, but relatively little iron, since the star is completely disrupted before its core can build up a large iron mass. So, the smoking gun would be an ancient second-generation star with a bizarre abundance pattern, rich in those lighter metals but curiously poor in iron. Finding such a star would be like discovering a specific type of shrapnel at an archaeological site, confirming the use of a particular devastating weapon. Astronomers are actively hunting for these chemical fossils in the halo of our own galaxy. A few candidates have emerged, stars with strange overabundances of lighter elements that defy explanation by normal supernova models. Each one is a potential message in a bottle, a relic that says, billions of years ago in your neighborhood, a titan died in the most complete and brilliant way possible. Confirming even one would not just solve a stellar mystery, it would prove that the universe's first acts of destruction were capable of a purity and power we can barely comprehend. The complete annihilation of a pair instability supernova left no central engine behind, but for other first stars, their deaths planted seeds of a different kind of cosmic monster, one that would become the universe's most brilliant beacon. This is the mystery of the first quasars. These are not stars at all, but the dazzling, hyperactive hearts of ancient galaxies. A quasar occurs when a supermassive black hole, sitting at the center of a galaxy, is surrounded by a vast, swirling disk of gas. As this material spirals inward at nearly the speed of light, it is compressed and heated to millions of degrees, glowing with a blinding intensity that can outshine every single star in its host galaxy combined. We have observed these cosmic lighthouses shining from when the universe was less than 700 million years old. Their existence poses the profound question of how a black hole grew to billions of solar masses in such a short time, a riddle we have already explored. But an equally pressing mystery surrounds their role as cosmic landlords. What was the impact of a quasar on its own galactic neighborhood? Imagine a newborn galaxy. its gas just beginning to cool and form its first generations of stars. Then, at its core, a quasar ignites. It floods the entire galaxy with a hurricane of ultraviolet radiation and X-rays, and often fires out jets of particles at near light speed that can punch clear through intergalactic space. This is an incredible amount of feedback. One school of thought sees this as a destructive, quenching force. The intense radiation heats the galactic gas, preventing it from cooling and collapsing into new stars. The relativistic jets can blow giant cavities in the gas, ejecting the very fuel for future stars out of the galaxy entirely. In this view, the quasar is a tyrant, shutting down star formation and placing a hard limit on how large its host galaxy can grow. But there is a competing and fascinating alternative. Could a quasar's fury actually be creative? The shock waves from its jets and radiation might slam into surrounding clouds of gas, compressing them so violently that they trigger a burst of new star formation, like a sonic boom creating a line of thunderstorms. The energy injection might stir the galactic pot, preventing the gas from settling into a quiet disk and instead keeping it dynamic and fertile. The quasar, then, would be both destroyer and midwife. Determining which effect dominated in the first galaxies is crucial because quasars were likely major drivers of reionization. Their brilliant ultraviolet light was perfect for stripping electrons from hydrogen atoms across vast distances. They may have been the blowtorches that carved out the largest bubbles in the reionizing foam, clearing the fog on a scale that even thousands of early stars could not match. Their dual nature forces us to see the early universe not as a peaceful place of gradual growth, but as a chaotic, feedback-driven arena where the most violent objects set the rules for everyone else. The first quasars did not just shine, they shouted, and the echoes of that shout determined the fate of everything that formed around them. The brilliant tyranny of the first quasars was just one force shaping the cosmic dawn. But to understand the full scope of that dawn, we must ask a fundamental question about its very nature. Did the end of the cosmic dark ages arrive as a sudden, universal flash or as a slow, creeping glow? This is a mystery of timing and texture, and the clues we have paint a complex, almost contradictory picture. On one hand, the ignition of the first stars required very specific conditions. A dark matter halo had to grow massive enough to pull in a critical amount of gas, and that gas had to cool via molecular hydrogen. This was not an easy or quick process, and it likely happened at different times in different parts of the universe. You can picture it as a vast, dark landscape where the first campfires are lit sporadically, in isolated valleys, separated by immense stretches of cold darkness. For millions of years, these lonely beacons might have flickered alone, their light swallowed by the surrounding fog before it could travel far. This suggests a slow, gradual dawn. Yet, the evidence from the cosmic microwave background tells a different story. The subtle patterns in its polarization, imprinted when free electrons scattered the ancient light, indicate that the universe was half reionized by the time it was about 500 million years old. This points to a relatively rapid process once it got going. So which is it? The key likely lies in a concept called positive feedback. Imagine one of those first isolated stars. It lives, dies, and explodes as a supernova. The blast does two things. First, it enriches the nearby gas with metals, making future gas clouds cool more efficiently and fragment into smaller stars. Second, the shock wave from the explosion can slam into neighboring clouds of pristine gas, compressing them and triggering a new round of star formation much faster than gravity could manage alone. That first star essentially builds a ladder for the next generation. Now, add to this the intense radiation from the first small galaxies and quasars, which can also compress gas on the edges of their bubbles. This creates a runaway effect. Once a region reaches a critical density of luminous sources, star formation can switch from a slow, sporadic trickle to a self-sustaining wave sweeping through the cosmic web. The transition from dark to light was probably both slow and fast. A long, hesitant period of isolated flickers was followed by a tipping point. Once enough first stars and galaxies had formed, their combined feedback ignited a chain reaction. Bubbles of ionized gas grew, merged, and eventually filled the universe. The data from quasar spectra supports this patchy model. The Lyman alpha forest shows a wide variation in the amount of neutral hydrogen along different lines of sight at the same cosmic time. Some paths are already clear, while others are still choked with fog. This is the signature of a gradual but accelerating process, not a single instant when a switch was flipped. Pinpointing the exact moment the universe became statistically bright is like trying to name the exact minute a night becomes morning. It depends on where you are standing and how you define the light. But solving this mystery is crucial because the speed of this transition directly tells us about the efficiency of those first stellar factories and the powerful, self-regulating feedback loops that they unleashed upon the newborn cosmos. The flickering dawn of the first stars raises a deeper question of companionship. Could those primordial giants have been born with partners, forming the universe's very first binary star systems? Modern simulations offer conflicting visions of that ancient nursery. In one view, the monolithic collapse of a vast, pristine gas cloud, hindered by inefficient cooling, funnels nearly all its material into a single, dominant core, resulting in a solitary titan. But other, more detailed models reveal a different possibility. As the massive cloud collapses, it can begin to spin, flattening into a swirling, turbulent disk around the central protostar. Within this violent disk, gravitational instabilities might cause it to fragment, spawning additional, smaller clumps of gas that could themselves collapse into stars. The result could be a small family of massive stars bound together in a tight, chaotic dance from birth. If binaries existed, their implications are profound. Two massive stars orbiting each other would exchange material, altering each other's growth and ultimate fate. Their lives could end in a spectacular merger, creating an even more massive star just before its death or in a double supernova. The gravitational waves from such a merger of first-generation black holes would be a unique signal from the dawn of time, a whisper of a partnership formed in the purest cosmic crucible. Yet for all their potential drama, these first binaries remain ghosts in the machine, their existence a critical unknown in the story of stellar beginnings. For every star that died in total annihilation, another left a lasting gravitational signature. Those first stars with masses between roughly 25 and 130 times our Sun likely met a different end. After exhausting their nuclear fuel, their cores collapsed under their own immense weight. The resulting supernova explosion would blast the star's enriched outer layers into space, but at the center, gravity won a permanent victory. The core crushed itself past the point of no return, forming a stellar mass black hole. These objects, perhaps 10, 20, or 50 times the mass of the Sun, were the universe's first permanent graves and also its most potent seeds. They sank to the hearts of their host dark matter halos, where they could begin a slow feast on any surrounding gas, or lurk quietly until a later merger provided more fuel. They are the hypothesized building blocks for the supermassive black holes we see later. But here lies the pivotal mystery, the initial mass function of population 3 stars. Simply put, how many stars were born at each possible size? Were they almost all unimaginable behemoths of several hundred solar masses, destined for pair instability destruction? Or was there a wider spectrum, with many stars in the lower range that left behind these black hole remnants? The answer dictates everything. It determines the chemical enrichment pattern we should find in ancient stars, the number of gravitational wave sources from the early universe, and the abundance of black hole seeds available to grow into quasars. It is the fundamental census of the first stellar generation, a lost piece of data that holds the key to understanding the balance between creation and destruction in the cosmos's first acts. That self-regulation of the first stellar nurseries is a cornerstone of cosmic evolution. The very processes that gave birth to the first stars also contained the seeds of their own limitation, a powerful balancing act known as feedback. When a massive population 3-star ignited, it did not just shine. It bombarded its surroundings with a torrent of ultraviolet radiation and powerful stellar winds, streams of charged particles flowing from its surface like a cosmic hurricane. This radiation was so energetic it heated the surrounding hydrogen gas in its host dark matter halo, making the atoms move faster and resist the pull of gravity. Think of it as the star turning up the thermostat in its own nursery, making the gas too hot and agitated to easily collapse and form new stellar siblings. But the most dramatic feedback came at the end of the star's short life. If it died in a supernova, the explosion did more than just spread new elements. It blasted the remaining gas clean out of the small, fragile halo. This is like a gardener who, after planting a single, magnificent tree, uses dynamite to clear the rest of the field, making it impossible to plant anything else for a very long time. This combination of radiative heating and explosive expulsion created a powerful feedback loop. A halo would gather gas, form one or a few massive stars, and then those stars would effectively sterilize their own environment, shutting down further star formation until more gas could slowly trickle back in, or until the halo itself grew much larger through mergers. This process likely made the first episodes of star formation incredibly inefficient and burst-like. It also helps explain why we do not see a universe filled with the descendants of those first monstrous stars. Their own brilliance cut their lineage short, ensuring the next generation would be built from their ashes, but on a more modest, sustainable scale. To uncover the specific details of that first generation, we must become cosmic archaeologists, digging for clues not in distant light, but in the ancient stellar ruins of our own galaxy. This is the field of galactic archaeology. Our Milky Way's halo, that vast, sparse sphere of stars surrounding the galactic disk, is a celestial graveyard filled with relics from the universe's infancy. Among the billions of stars there, astronomers hunt for the rarest of treasures, ultra-metal, poor stars. These are suns with such minuscule amounts of elements heavier than helium that they must have formed very early, from gas enriched by only one or two previous supernovae. A star like SMSS J03 1300.36-6708339.3 is a legendary example. Its iron content is less than 1/10,000,000th that of our Sun, but it shows a surprising abundance of carbon. This bizarre chemical fingerprint is a forensic snapshot. It tells a story where this star formed from a cloud of gas polluted by the debris of a single, first-generation star. The specific pattern, lots of carbon but almost no iron, is like a signature. It points strongly to the death of that first star being a faint supernova, one where the explosion was just powerful enough to eject the outer carbon-rich layers, but where the iron core fell back, swallowed by a black hole. By reading these elemental runes in the light of a single, ancient star, we can effectively reconstruct the mass, life, and death of a specific population 3-star that died over 13 billion years ago. Each of these stellar fossils is a time capsule with a unique message, allowing us to conduct an autopsy on the universe's first giants, one chemical element at a time. Those stellar fossils reveal the chemistry of the first stars, but they say nothing about another invisible force that might have shaped their birth. Magnetic fields are the silent architects of our modern cosmos, guiding the collapse of gas clouds and launching powerful jets from young stars. But their origin is one of the great unsolved puzzles of the early universe. Did magnetic fields exist at cosmic dawn? If so, where did they come from? One possibility is that they are primordial, woven into the fabric of space-time during the universe's explosive first moments, perhaps during a period of rapid inflation. These seed fields would have been incredibly weak, a faint cosmic whisper but stretched across the entire cosmos. The other leading idea is that they were generated later, locally, by the first structures themselves. As turbulent gas swirled around the first protostars or through the disks of the first galaxies, it could have acted as a natural dynamo, amplifying any tiny, random magnetic fluctuations into organized fields. The distinction is crucial. A pervasive primordial field would have been a universal player from the very beginning, gently influencing how the first gas clouds fragmented and collapsed, potentially affecting the ultimate size of the first stars. A later, localized origin means magnetism was a consequence of structure, not a cause, emerging only after the first luminous objects had already begun to shine. We may never detect those first feeble fields directly, but their ghostly influence could be imprinted in the polarization of light from the cosmic microwave background or in the magnetic properties of the oldest gas clouds we can observe. Their presence or absence changes the physical conditions of the cosmic nursery in a fundamental way. This leads to a question that stretches the imagination to its limit. In those first metal-free stellar systems, could there have been planets? Our standard recipe for planet formation is absolutely dependent on dust. Tiny grains of silicon, carbon, and iron forged in stellar furnaces clumped together to form pebbles, then rocks, then planetary cores. Around a pure population 3-star, this ingredient was completely absent. There was no dust, no soot, no solid material of any kind beyond hydrogen and helium gas. So, a rocky world like Earth was an impossibility. But what about a gas giant? Consider a theoretical scenario where a massive population 3-star has a lower mass binary companion. As the system forms, a swirling disk of pristine gas could develop around one or both stars. Within that disk, a new kind of instability might take hold. Without dust to help it cool and contract, a clump of pure hydrogen and helium gas would need to rely solely on its own gravity to overcome the gas's internal pressure and heat. It is an extreme and fragile process, but some calculations suggest it is not entirely impossible. The result would be a protoplanet, a globe of primordial gas collapsing directly from the disk. This would not be a Jupiter as we know it. Jupiter has a core of rock and ice. This first-generation gas giant would have no solid core at all. It would be a pure hydrogen-helium atmosphere all the way down, becoming denser and hotter until the pressures turn the gas into a strange metallic fluid. It is a world with no surface, no chemistry beyond the simplest molecules, and no possibility for life as we understand it. It would be a hauntingly beautiful relic, a cosmic fossil preserving the exact composition of the universe's first gas, orbiting the brilliant, brief fire of its monstrous sun. While the odds of such a world forming are vanishingly slim, and detecting one is beyond our current imagination, the possibility forces us to reconsider the boundaries of what is possible. It asks if the first cosmic architectures, built from only 2 elements, could have achieved a complexity we never thought to look for, creating silent, gaseous companions to the universe's first and most brilliant lights. These silent, gaseous worlds would have been fleeting phantoms dissolving with their monstrous suns, but other relics from that era are far more tangible, and they are hiding in plain sight, orbiting our own galaxy. This brings us to our 22nd mystery, the ultra-faint dwarf galaxies. These are the smallest, faintest, and most ancient galaxies we have ever discovered. Imagine a galaxy so dim it contains only a few thousand stars, lost in the vast halo of the Milky Way, its light drowned out by the brilliance of our own galactic center. Yet within these feeble smudges of starlight, we may have found the universe's most pristine living fossils. The stars in these dwarfs are almost pure hydrogen and helium, with metal contents hundreds of times lower than stars in the main disk of our galaxy. They are not just old, they are primordial. This suggests these tiny galaxies are not fragments torn from a larger galaxy, but survivors. they are likely some of the very first structures to ever form tiny dark matter halos that manage to gather just enough gas to spark a single, brief burst of star formation over 13 billion years ago and then stop. They have been essentially frozen in time ever since, orbiting the Milky Way like cosmic time capsules. Studying them is like an archaeologist finding a perfectly preserved Neolithic camp, untouched by later civilizations. By analyzing the motions and chemistry of their ancient stars, we can infer the properties of the tiny dark matter halo that cradles them, giving us a direct measurement of the smallest scales of structure in the infant universe. They are our closest link to the epoch of the first galaxies, a population of celestial relics that never grew up. But this reliance on what we can see locally leads directly into a profound and unsettling 23rd mystery, the problem of cosmic variance. Our most spectacular views of the early universe come from deep fields, like the iconic Hubble Ultra Deep Field. In that image, Hubble stared at a seemingly empty patch of sky for days, collecting the faintest photons to reveal thousands of galaxies stretching back to the cosmic dawn. It is a breathtaking window into the past, but here is the catch. That field of view is incredibly narrow. It covers an area of sky roughly equivalent to a grain of sand held at arm's length. We are looking at the universe through a pencil-thin straw. The fundamental question is whether this tiny, magnificent snapshot is truly representative of the whole cosmos at that time. Was the distribution of the first galaxies smooth and uniform, like sprinkles evenly scattered on a cupcake? Or was the early universe a patchwork quilt of light and darkness, with brilliant clusters of early stars separated by vast, empty voids that were still languishing in the cosmic dark ages? Our entire understanding of the timeline of reionization and the growth of structure is built on these precious but limited samples. If we happen to point our most powerful telescopes at an unusually dense region, we might conclude star formation started earlier and more vigorously than it really did across the universe. Conversely, if we looked at a cosmic desert, we might think the dawn was delayed. This is cosmic variance, the statistical uncertainty that comes from observing only a small fraction of the whole. It is a humbling reminder that our entire cosmic story might be written from the perspective of a single, random paragraph in a book of unimaginable length. The only way to overcome it is to look farther and wider, to map more of the sky with the same incredible depth, to see if the story told by one grain of sand matches the story of the entire beach. Until we do, a shadow of doubt will always linger, a whisper that the dawn we think we see might just be the glow from our own neighborhood window. The possibility of cosmic variance forces us to question our most basic assumptions, but there is another assumption about the first stars themselves that is beginning to crack. We have long pictured them as solitary titans born alone in monolithic clouds, yet newer, more powerful simulations are revealing a different, more dynamic nursery. When astronomers run these digital models with higher resolution, they see something fascinating happening in the swirling accretion disk feeding a newborn population 3-star. The disk itself, a maelstrom of hot, pristine gas, can become gravitationally unstable. It doesn't just feed the central star, it can ripple and fragment, spawning additional, smaller clumps of gas that collapse into their own stars. The result is not a single behemoth, but a small, tight-knit family of massive stars, a true first-generation star cluster. This is a paradigm shift. If the first stars often formed in groups, it changes everything we thought we knew. The chemical enrichment of the early cosmos would be more complex, as multiple supernovae from the same cluster would pollute their neighborhood with a mixed signature. The feedback would be more intense and concentrated, as several brilliant stars would heat and blow away their shared gas cloud simultaneously. Perhaps most intriguingly, it raises the chance for stellar interactions. In a dense cluster, these massive stars could gravitationally tug on each other, exchange material, or even merge, creating even more bizarre and massive objects just before their explosive deaths. The monolithic model painted a simple picture of isolated giants. The cluster model suggests the cosmic dawn might have been a more crowded, chaotic, and interactive party than we ever dreamed. And the death of one of those first massive stars, whether solitary or in a cluster, could have produced the single most luminous event since the Big Bang itself. We call them gamma-ray bursts, or GRBS. These are fleeting, blinding flashes of the highest energy radiation, often lasting only seconds, but outshining entire galaxies for that brief moment. The long-duration type is intimately linked to the death throes of a massive star, specifically when its core collapses to form a black hole and powers two ultra-relativistic jets that punch through the star's outer layers. If a jet is pointed directly at Earth, we see the incredible flash. Now apply this to a population 3 star. Imagine a monster of pure hydrogen and helium, hundreds of times the mass of our Sun, reaching the end of its life. Its core collapse would be cataclysmic, and the jets it might produce could be unimaginably powerful. A population 3 gamma-ray burst would be the ultimate cosmic beacon, a flash of light so brilliant it could pierce the obscuring fog of the early universe and be visible to us today across a gulf of over 13 billion years. The mystery is whether we have already seen one and not known its true origin. Our telescopes like Swift and Fermi detect gamma-ray bursts almost daily, but pinpointing their distances is tricky and often delayed. Finding a GRB with a redshift so high it places it squarely in the era of the first stars would be a discovery of monumental importance. It would not just be a point of light, it would be a direct, real-time transmission of a first star's death scream, carrying encoded information about its mass, rotation, and environment. We would be witnessing, in a single brilliant flash, the final act of a cosmic pioneer, a signal from the very edge of time confirming that the universe's first lights did not fade quietly, but went out with the most spectacular bang imaginable. The death scream of a gamma-ray burst scattered more than just light, it scattered the very seeds of solidity. Those cataclysmic explosions did not just create new atoms, they forged the universe's first dust. This is a mystery of microscopic construction on a cosmic scale. In the pristine environment around a population 3 star, there were no solid particles, not a single speck. Dust, the tiny grains of silicon, carbon, and iron that are so common in our galaxy, simply could not exist. The first dust grains had to be manufactured from scratch, and the factory was the violent aftermath of a star's death. In the expanding, cooling ejecta of a supernova, atoms like carbon, silicon, and iron, freshly forged in the explosion, could bump into each other and stick together in the vacuum of space. Think of it as soot forming in a cosmic chimney. These initial clusters, perhaps only a few dozen atoms across, were the universe's very first solid things. Another production line opened in the atmospheres of later generations of aging stars. As these stars evolved, they blew strong winds off their surfaces, and in these cooler, denser winds, atoms could condense directly into dust grains. This stardust was then blown into space, a gentle sprinkle compared to the supernova's blast. But why do these microscopic particles matter so much? Because dust is a cosmic coolant. A tiny solid grain has a much larger surface area than a single atom, and it can radiate heat away as infrared light far more efficiently than hydrogen gas ever could. Once dust entered the cosmic ecosystem, it revolutionized star formation. Gas clouds could now cool, fragment, and collapse into many smaller, longer-lived stars like our Sun. The era of the solitary titan was over, replaced by a bustling, efficient stellar economy. Pinpointing the exact moment dust first appeared is like finding the first spark that lit a new industrial age. We search for its signature in the most distant galaxies, a faint reddening of their light as dust absorbs and re-emits starlight. Finding dust in a galaxy from the universe's first billion years tells us that the alchemical transition from pure gas to solid complexity had already begun. That dust helped build new stars whose light then began to carve permanent homes in the primordial fog. The epoch of reionization was not a gentle, uniform sunrise. It was a patchwork of brilliant bubbles growing in the darkness. Picture the early universe not as a homogeneous soup, but as a vast, dark Swiss cheese. Each hole in that cheese is a bubble of ionized hydrogen, a region where the ultraviolet light from an early galaxy or quasar has stripped electrons from every atom, burning away the opaque neutral gas. Around a single, faint early galaxy, the bubble might be small, perhaps only a few thousand light-years across. But around a brilliant quasar, the bubble could be colossal, an ionized cavern stretching for millions of light-years. The mystery lies in mapping the growth of this bubbly structure. Did reionization proceed democratically, driven by billions of small galaxies, their modest bubbles slowly swelling and merging like soap suds in a sink? Or was it an aristocratic process, dominated by a few rare, brilliant quasars whose enormous bubbles punched through the fog early on, dictating the large-scale geometry of the transparent universe? The size and distribution of these bubbles is a direct record of the power and number of the first light sources. Astronomers hunt for this bubble structure in the Lyman alpha forest. If the light from a distant quasar passes through a large ionized bubble, there will be a clear stretch in its spectrum, a gap in the forest where no neutral hydrogen exists to absorb the light. By measuring the size of these gaps along many different lines of sight, we can begin to reconstruct the three-dimensional sponge of the reionizing universe. The answer will tell us if the cosmic dawn was a collective effort or a story of brilliant, isolated tyrants whose light cleared the way for all that followed. The universe's first starlight did more than illuminate. It carried a hidden command that could stifle the birth of future stars across vast distances. This subtle but powerful form of feedback is known as the Lyman-Werner background. The first massive stars blazed with intense ultraviolet radiation, and within that glow were photons at very specific energies, corresponding to what astronomers call the Lyman-Werner bands. These particular photons had a unique and destructive power when they traveled across the early cosmos and struck a distant cloud of pristine gas. Inside that cloud, the fragile molecular hydrogen molecules, the only coolant available, could absorb this radiation. The energy from the photon would break the bond holding the two hydrogen atoms together, dissociating the molecule back into solitary atoms. This process, photodissociation, was a cosmic sabotage. By destroying the molecular hydrogen in a neighboring gas cloud, the radiation from a first star could rob that cloud of its ability to cool down. Without cooling, the cloud could not condense and collapse under gravity. It was left in a kind of suspended animation, too warm to ever ignite its own stellar fire. A brilliant beacon in one dark matter halo could therefore cast a long shadow, preventing star formation in halos nearby, effectively regulating the pace of the cosmic dawn across millions of light years. It was feedback without a blast wave, a silent veto written in ultraviolet light. This gradual stifling of the first generation was part of a larger transition, the final fate of the population 3-star era. Their reign, though brilliant, was always destined to be short. Each massive star that lived and died performed that crucial act of alchemy, seeding the cosmos with metals. Once even a trace of carbon, oxygen, and silicon existed in a gas cloud, everything changed. These heavier atoms are far more efficient at radiating away heat than molecular hydrogen ever was. A cloud enriched with metals could cool rapidly, fragment into many smaller clumps, and collapse into stars that were much less massive than the primordial titans. This gave rise to the next stellar generation, population 2 stars. These stars could have masses similar to our Sun, burning for billions of years rather than just millions. With their birth, the chaotic, explosive era of the solitary giants came to a close. The universe shifted from a frontier of brilliant, short-lived behemoths to a more stable, complex economy of smaller, longer-lived suns. The boundary between the population 3 and population 2 eras is not a sharp line in time, but a fuzzy, gradual transition that played out differently in different corners of the cosmos. In some regions where early supernova enriched the gas quickly, the age of monsters might have ended after just 1 or 2 generations. In more isolated voids, pure population 3 stars might have continued to form for a bit longer until the metal pollution finally spread. We are still trying to illuminate this cosmic shift, searching for the last of the pure giants and the first of the enriched stars to map the moment the universe settled into the familiar rhythm that would eventually lead to stars like our own and to planets that could harbor life. That faint radio whisper from the dawn may have already spoken, and its message defies everything we thought we knew. This brings us to our final and perhaps most urgent mystery, the cosmic dawn signal anomaly. We touched on it earlier with the EDGES experiment, but the full story is a scientific cliffhanger. In 2018, a small, unassuming radio antenna in the remote Australian outback reported something extraordinary. The experiment to detect the global epoch of reionization signature, or EDGES, was designed to listen for the subtle 21-centimeter hum from the universe's infancy. What it found was not just a signal, but a profound puzzle. The data revealed a deep absorption trough in the radio spectrum, a fingerprint from when the universe was only about 180 million years old. This was expected, but the depth of the dip was shocking. It was twice as strong as the most optimistic theoretical models allowed. The primordial hydrogen gas, it seemed, was astonishingly, inexplicably cold. In the standard story, this gas should have been gently warmed by the faint afterglow of the Big Bang, the cosmic microwave background. To be so cold, it must have lost its heat to something else, something even colder. The most thrilling explanation points a finger at the universe's greatest enigma, dark matter. What if, in that ultra-dense early cosmos, dark matter particles were not just ghostly spectators? What if they could bump into hydrogen atoms like 2 different gases slowly mixing, and in doing so siphon away heat? This interaction would have chilled the hydrogen dramatically, creating the deep absorption signal EDGES observed. It would be the first non-gravitational detection of dark matter in history, a discovery that would shatter the standard model of particle physics and rewrite the rules of the cosmos. Yet here we are, years later, and the mystery remains in a tense limbo. No other experiment has been able to definitively confirm the EDGES result. The scientific community is divided, caught between the breathtaking potential of the finding and the sobering possibility of a subtle systematic error. Could the signal be an artifact of the instrument itself, or a tricky interference from the local environment on Earth? The antenna was meticulously designed and tested, but the signal is so strong that many experts find it hard to believe it has been missed by the universe itself. Resolving this anomaly is now one of the highest priorities in cosmology. New and more sensitive experiments are coming online, each with different designs to cross-check the result. The upcoming square-kilometer array, a continent-spanning radio telescope, will have the sheer power to map this signal across the sky, leaving no room for doubt. So we stand at a crossroads with 3 possible paths. The first is a letdown, a simple calibration error that closes a fascinating but false lead. The second is monumental, the confirmed first direct detection of the cosmic dawn, a radio photograph of the universe's first starlight. But the third path is revolutionary. It would mean that EDGES did not just hear the first stars, it heard the whisper of dark matter interacting with the newborn cosmos. It would be a message from the dawn, written in a physics we do not yet understand, telling us that the story of the first stars is intertwined with the nature of the universe's deepest secret. The antenna in the desert listened, and it heard a note that does not fit the song. Now the entire world is leaning in, waiting to hear if it was a mistake, a melody, or a key to a completely new symphony. So the universe's first song may still be waiting for its final verse. After exploring 30 cosmic puzzles from the silent dark ages to the explosive deaths of the first stellar giants, one truth stands clear. Each mystery is a humbling reminder of how much we have yet to learn about our own origins. This is not a finished story sitting in a textbook. It is a living narrative, unfolding in real time through the lenses of our most ambitious machines. The search for these answers is what launched the James Webb Space Telescope, an instrument that is, at this very moment, peering into that ancient era with unprecedented clarity. Its infrared gaze is sifting through the cosmic static, looking for the faint red smudges of infant galaxies and dissecting their light for chemical clues. What will it find? Perhaps a direct image of a first galaxy caught in the act of formation, its shape a testament to the violent physics of the early cosmos. Or maybe, hidden in the spectrum of an impossibly ancient star, the unique chemical signature of a pair instability supernova, the ghostly fingerprint of a titan that died in total annihilation. Every new observation, every faint pixel of data from the edge of time adds another piece to the puzzle. We are cosmic cartographers drawing the map of a forgotten age. The story of the first stars and galaxies is still being written, and we are the ones holding the pen. Which of these 30 mysteries captures your imagination the most? Is it the ghostly radio signal that might whisper of dark matter, or the brilliant, fleeting flash of a first star's gamma-ray burst death? Let me know in the comments below, and if you want to join the next deep dive into the cosmos's greatest secrets, be sure to subscribe.